Hello everyone, my name is Z. I'm here to present you our 466 project, CAPTCHA Images Decoder. Here's the content for this video, introduction, data, and explanation of our 4 algorithms, and comparing the results of the 4 algorithms, and finally a conclusion. So what is CAPTCHA? CAPTCHA stands for Completely Automated Public Tuning Test to Tell Computers and Human Apart. CAPTCHA has been a popular method to distinguish between robots and human users. I'm sure everyone watching this video have to experience CAPTCHA when they log onto some websites. So our goal in this project is to use different algorithms to decode and recognize the text-based CAPTCHA images and compare each of the algorithm performance. Our data is comprised of 10,000 CAPTCHA images of size 200 by 50 pixels. The dataset is generated using Google CAPTCHA's library by one of our group members. For this recognition problem, which is a supervised classification problem, the labels of our data are multi-class. There are a total of 36 classes, which contains 10 digits and 26 case-insensitive letters. For all models, include segmentation-free and segmentation-based models, we use the same approach to evaluate the performance of the models. All models are evaluated for performance using accuracy, and the higher the accuracy, the better the model. In addition, we consider the model prediction accuracy only when the model successfully identifies all characters inside the CAPTCHA. This is because in practice, textual CAPTCHA is only passed when all the inputs are correct. So the first method we try is the convolutional neural network, CNN. For CNN, it has two main features. First, it can effectively reduce large data volumes to small data volume. Second, at the same time, it can retain image features. In this project, we built a CNN model with 10 hidden layers, as shown in this diagram. Include 4 convolutional layers, 4 pooling layers, and 2 fully connected layers. The model works with value activation function and will output a sequence of length 216 for character prediction. For the flow of data for CNN, the model will take the image directly as input, and after a series of convolution pooling operations, the model will output a sequence of length 216. This sequence will be divided into 6 equal segments of length 36. This is the same as the number of labels we have. We obtain the labels of the corresponding index according to the index of the maximum value in each segment. Finally, these labels will form a 6-digit CAPTCHA. Another segmentation-free model we want to try is the recurrent neural network, RNN. By applying this method, we are trying to introduce the potential of a model to solve the extended problem of recognizing variable length CAPTCHAs. However, in our experiments, it turns out that the traditional RNN model acts poorly on this image recognition problem, even if the hyperparameters are properly tuned. After 100 epochs, its prediction accuracy is only 0.02%, so we decided to use a variance of RNN, the encoder-decoder RNN model. This model we implemented contains 2 RNN units. One of them serves as the encoder that encodes the input sequence into a hidden fixed-length vector, while the other is the decoder that maps the vector into output sequence. Here is the flow of data for RNN if you are interested to get into more details. The flow of data of our segmentation-based models, support vector machine and k-nearest neighbors, we have to first perform image preprocessing and character segmentation before applying the algorithms. After usual image preprocessing, the rudimentary image segmentation techniques simply straighten the image and divide it into 6 parts evenly and ditches the rest of the white background. Here is an example of the CAPTCHA image after preprocessing and segmentation. The first segmentation-based algorithm we explore is the support vector machine. It has 2 hyperparameters, a regularization parameter which controls the strength of the regularization, and kernel types exploited in the model. We explore a couple of different regularization parameters, each with kernel types linear kernel, polynomial kernel, and radial basis function kernel. The second segmentation-based algorithm we explore is the k-nearest neighbors, KNN. The KNN algorithm classifies each unknown class based on the most common class of its k closest distance neighbors. The distance can be calculated using one of the many common distance measures, like Manhattan, Euclidean, or Hamming distance. Here's just an example of how the algorithm works. Here's the unknown class we try to classify. If we pick k equal to 8, then it will be classified as blue, since blue is the most common class of its 8 neighbors. If we use k equal to 16, then it will be classified as green instead, since now green is the most common class among its 16 neighbors. Let's move on to the results section of the algorithms. Here is a performance chart of the two neural network algorithms. According to the experiments, the CNN model performed well in this project, and the accuracy can reach about 97% after 15 training epochs. And according to the experimental result, we found that the CNN model is more resistant to default type of noise. We think one of the reasons is the presence of convolutional operations in the CNN model. It can extract the needed features in the data and reduce the impact of interference on character recognition, while still preserving the location information. Thus, CNN model can get a good performance on CAPTCHA recognition. For the RN model, the accuracy converges about 70% after 40 epochs, indicating that RN model is considerably weaker than the CNN model. One possible reason for this poor performance is that, unlike what the CNN does in the convolutional operations, the RN fails to reserve the spatial properties of the input image, which are usually the essential hidden features of the input in any image recognition problems. For the results of support vector machine, the maximum accuracy is around 80%. From the results, we found out that choosing the right kernel type is very important in this algorithm. In this chart, we can see that the kernel type is very crucial. The kernel type that works the best is the radial basis function kernel, which you can reach around 80%. The worst one is the linear one, which the highest is around 43%, 45%. The regularization parameter doesn't matter as much when it gets bigger than 1. The results for k nearest neighbors, the maximum accuracy is around 72%, with k equal to 20 neighbors. K here is a hyperparameter we tried out with different values. And this algorithm is highly susceptible to noise. What this means, I will show you in the performance chart. Here's the KN performance chart. The orange one is with noise reduced. The gray one is with no noise reduced. As we can see, there's a big gap in the performance. Moving on to the conclusion section, we can conclude that the CNN model performed the best in our project. It can reach a maximum accuracy around 97%. The other three algorithms have a maximum accuracy between 70 to 80%, which is not bad, but there's still room for improvement. For future work, we plan to explore which noise the model is more sensitive to in order to obtain a certain level of interpretation. We also want to design some experiments to discover the reasons behind the aforementioned results and verify our hypothesis. For example, to design some experiments to verify the effect of spatial properties of the image on the performance of the models. And this is the end of our presentation. Thank you for watching.